Swayam Prabha. Digital India. Educated India.
Okay, today we are going to talk about strengthening and corrosion in metals. So, we have gone through various types of metals and metallic alloys, and we have already seen that the alloys are created with an intention to actually improve the properties of a metal. So, there are some basic techniques towards this, which I will be talking about when I will discuss about the strengthening of metals. Now, also because of the basic metallic nature, there is there are always susceptibilities to different kinds of corrosive environments. So, that also we will talk in this second section of it. So, both strengthening and corrosion of metals is what we are going to discuss today. Okay. So, strengthening mechanisms in metals, corrosions in metals, and some of the corrosion types and their prevention. This is what is our object of study today. Now, first of all, the strengthening mechanisms in metals. One thing we have already seen that dislocations, if it is present in a metal, then it actually degrades the material properties. Now, as long as the dislocation is actually limited inside a particular grain, there is no problem in the sense that it will, the macroscopic properties will not be that much affected. But if there are many grains which gets affected by dislocation, all adjacent grains, then actually that would substantially affect the mechanical properties. So, the ability of a metal to plastically deform depends on their ability to dislocate and these dislocations to move across the grains. And if you can stop this movement across the grains, then you can make a material harder and stronger. And there are several ways by which we can do it. One is through the grain size reduction, then the other one is a solid solution strengthening, and then of course there is strain hardening, then there is precipitation hardening, etc. So, let us try to look on some of them one by one. So, first of all, we discuss about the grain size reduction. Now, the grain boundary acts as a barrier for dislocations that we have just now said, but how does it act as a barrier for dislocation? There are two reasons by which it can happen. One is that there is the misorientation, that means if two grains are there and these two grains are not oriented, their lattices are not oriented, then it will be difficult for a dislocation to pass into another grain. Okay. So, if there is a loss of alignment between the two grains, the lattice structure of the two grains. Okay. So, suppose in this particular example, you consider these to be one grain and then you have this one, the two lattices are not aligned. Okay. So, there is an angle. So, then it will be difficult for a dislocation to move from this to the next lattice. So, that is what is called misorientation. Now, you imagine that in terms of number of grains in a particular surface area, if you have more and more and more of these grains, okay, which are misoriented with respect to each other, then it will be more and more difficult for the dislocation to affect all of them in a kind of a statistical scale. So, the more it will face these grains, the more difficult it will be for the dislocation to pass. So, that is one of the reason why smaller grains, that means more grain boundaries, would actually stop the dislocations very effectively to move across the grain boundaries. The second one is the atomic disorder. because we near or within a grain boundary region, this atomic disorder generally leads to a discontinuity of slip planes from one grain to the other. So, that is also another possibility where the dislocations would not be able to move. There is also another third possibility, that means and it is actually more it starts not with the dislocations, but with the point defects, that inside a grain the probability of having a point defect at a particular point is not the same in the next grain. So, as a result, the piling up of the this kind of defects or dislocations, that is not possible uniformly across all the grains. So, if there are more number of grains, the less the probability that dislocation pile has occurred in all of them at the same uniform rate, and hence the dislocations movement would be lesser and lesser. Now, a fine grain material is then harder and stronger than a coarse grain material, and due to, as I said, the great the larger grain boundary area to restrict the dislocation motion. This was first observed by Hall in Sheffield, in University of Sheffield, close to 1950s. Hall has observed this first in steel alloys, and later on independently Pech has also observed the same, not for steel alloys, but for other alloys. So, what Hall noticed is that the relationship between the yield strength and the average diameter d actually follows this kind of a nonlinear relationship between the average grain diameter and the yield strength, and there are two constants sigma 0 and ky which governs these relationships. Okay. Interestingly, that is the same thing Pech has later on seen, that is not only for mild steel, but for other materials also this same thing happens, and people have found out through experiments the values of these Hall-Pech constants, like for copper it is sigma 0 is 25 MPa, and the K is about 0.11 MPa meter to the power half, or titanium it is 80.4, mild steel 70.74, Ni3Al it is 300 and 1.7. Now, one important thing is that it is the K which actually kind of determines that how much of the effect of D will be on the overall sigma y. Okay. So, suppose if I consider the mild steel, okay, and I have considered here the diameter of the grain from about 100 nanometer to about 1000 nanometer, and I have considered these values of sigma 0 and K as 0.74, which means my sigma y is actually 70 plus 0.74 d to the power minus half, and then I have given all these values. Okay. So, we can really see, yes, that the sigma y as the grain size is increasing, okay, even though not at a very high level, but it is indeed decreasing sigma y. So, the Hall-Pech constant very nicely describes how the mild steel is actually the grain size affects the strength of mild steel, and similarly for the other alloys. Now, let us talk about another form of strengthening. Okay. So, that is known as the solute solution strengthening. So, in this case the strengthening is occurring because there are so called pinning of impurities, okay, inside the grain, and which actually stops the growth of the dislocation or the dislocation piling. So, in fact, you would see that pure metals, that is why are almost always softer than their alloys. Why? Because these alloys, I have talked earlier about for example, these substitution of the alloy atoms, right, the alloying atoms in a solid solution, right, in the interstitial spaces, for example. So, whenever these impurities goes in the interstitial or substitutional positions, then what happens? Either if they are actually the atoms are actually on the host atoms, if the atoms that goes inside, if they are larger in size, then there will be a compressive strain which will be developed in it, and on the other hand tensile strain will be imposed on host atoms by smaller impurity atoms. So, larger atom size of atoms will give a compressive strain, because it is taking more space. So, it is actually pushing all the other atoms inside the grain. So, there is a compressive strain, and if you put a smaller one, then others are also coming towards it to and as a result there is a tensile strain. In both the cases, thus you can actually influence the dislocation stress, which is actually denoted by the Berger's vector. So, you can influence it with the help of the impurities. So, thus basically the impurities actually can anchor very effectively these dislocations, and that is why alloys are generally much stronger than the pure metals. Like you can consider nickel weight percentage, okay, and as you can see that here the tensile strength, as the nickel alloying is increasing in copper, you see the tensile strength is actually increasing, and also its elongation is decreasing, because it is becoming harder and harder. Okay. So, that is another strategy of making materials, the pure metals, harder by inserting impurities. Now, we will talk about strain hardening. Now, strain hardening is, so in the other cases you are actually playing with the what you call the grain structure, but here you are not doing that. You are actually using a mechanism in such a manner that you are applying the work hardening or cold working, okay, so that there is a strain that you are imposing on the nearby atoms inside the grain structure, and thus you are actually increasing the strength of the material. Now, that strain increases the so called the strength, that you must have seen that in the stress strain diagram itself, when beyond a certain percentage of strain, there is a strain hardening area that occurs. Okay. So, the idea is very much similar, but in the formation of the metal itself, this particular technique is thus used, and the hardening happens to the system. And there are for example, you can see here that the percentage of cold work, okay, how it is changing the strength, okay, or how while increasing the strength, how you are actually strength is increasing, but the ductility is actually sacrificed in this process. And you can actually measure the percentage of cold working. If you know the original area and the deformed area, then you know how much percentage of cold working has taken place, and there are ready-made charts available from which you know that how much of strength increase you can expect from the strain hardening. Now, the strength that is increased can sometimes be controlled also by actually annealing. So, that is what is actually a heat treatment process, okay. Through a slow heating and slow cooling, you can actually release some of it, okay, and thus you can control you can bring a trade off solution between the strength and the ductility of a system. So far we have discussed three methods, right. One is the refining of the grain boundaries, as these grain boundaries serve as barrier to dislocation motion. So, by having a more refined polycrystalline material, you can increase the strength. Of course, there is a degree up to which you can do it. In fact, later on there is it's called a reverse Hall patch effect, that people found out that if you reduce the grain structure beyond a certain level, okay, then this becomes counterproductive, and it actually so it actually depends on the size of the dislocation. Okay. If suppose the size of a dislocation is 10 nanometer, and if you are bringing your grain structure of a similar level, then the dislocations, it would not be difficult for the dislocations to actually get piled up across the grains anymore, and hence instead of increase of the strength, you may see the decrease of the strength. So, the reverse effect may happen if you reduce the grains too much. So, there is an optimal level of grain size for every metallic system. Then the second way of doing is of course solid solution strengthening, which is with the addition of the impurity. And as we have shown you earlier, that both of these solid solution strengthening and strain hardening, they are also there are these two counter objectives, that for while adding impurity or while increasing the percentage of cold work, you are actually strengthening the system, but you are sacrificing the ductility. So, you have to take a rational decision towards it. There is another effect which is considered in many industries, that is very popular, is known as precipitation or edge hardening. So, what is done in this case is, so far temperature has not really considered in this entire scenario, but if you bring temperature, then actually the phase boundaries come into picture, because every impurity, their solubility changes as you are changing the temperature. So, based on the changes in solid solubility with temperature, you can actually produce fine particles of an impurity phase, and which can block the movement of dislocation. So, for example, at a slightly higher temperature, you may see that there can be more impurities that can be spreaded over inside a pure metal, and they act like nucleation points, and then as you keep it at a very low cooling rate, gradually what happens is that these impurities actually affect the grain formation, and as a result it affects the hardening. So, this temperature and to change the solubility and later on allowing more time for the grains growth actually is known as the aging. So, edge hardening, precipitation and edge hardening, these two things actually go hand in hand. So, this is another mechanism in terms of controlling the hardening, okay, of pure metal. Now, these are so far whatever we have discussed are related to the improvement of the metal. However, the metals also suffer from a problem, the ceramics would not suffer from it, that they get corroded. Okay. I have talked about it in the very beginning. If you remember, I have shown you the periodic table and I have shown you the relative positions of the metals, okay, that their tendency to giving away the electrons. Okay. So, as a result of this tendency, they can easily actually react with the environment, and those inorganic materials which can absorb these electrons, they can quickly react with these metals, and this results in corrosion. And these corrosions are definitely, they are destructive, they are unintentional attack on structures, and they are basically electrochemical in nature. You can see the corrosion of a ship or an automobile or a pipeline. In every case the corrosion creates a severe problem. Now, the material loss that takes place can be either through dissolution or through formation of scale or a film. Okay. So, that means the reaction takes place and the compound actually forms over the surface like a film or a thin scale. For example, you take an aluminum vessel, okay, and you put water in it and then you try to heat it up, and you do this for several times, you will gradually see that there will be a layer of aluminum oxide which will be formed over aluminum at a higher temperature, and that will come like a green sheet over the aluminum. So, like a thin scale or film. There are various ways in which this takes place, and there is approximately 5%, even higher in some cases, of industrialized nations income which is generally spent for the corrosion prevention, maintenance, etc. So, that means it is a big issue for various systems. Now, there are two parts of these kind of chemical corrosions. One is the oxidation reaction or anodic reaction. In this case, this is related to the tendency of the metals to actually give up the free electrons, and the other is the cathodic part, which is just the opposite part of it, where electrons are transferred to another chemical species based on their position in the periodic table, that they will be able to accept the electrons. For example, zinc. Okay, so zinc can readily give up 2 electrons, and this can be taken up by hydrogen, and hence the moment you keep zinc, there will be a zinc converted to zinc ion, and hydrogen gas will be formed. In fact, many a times that is why zinc is given as a sacrificial layer coating. So, that let that very readily react and save the metal. So, I will talk about it, that what is the significance of this type of layers. Now, when we select as a result such material to provide a protective layer over the original material, there is something called as a piling bedworth ratio, PB, okay, which is nothing but the volume of the oxide that is forming during reaction to the volume of metal that is consumed in the oxidation. So, if suppose the PB ratio is greater than 2, what does it mean? It means lot of oxides are getting formed and relatively less amount of metal is consumed in the oxidation. Okay. So, as a result, what will happen is that there will be high compressive stresses in the oxide film, and because the volume of oxide formed is quite high, and there will be oxide cracks and flaking off, and this material then cannot be used as as a protective material because of its tendency to develop cracks and flaking off. If PB ratio is less than 1, that would mean that the volume of oxide formation is smaller in terms with respect to the volume of metal consumed, and that will create another type of trouble where actually tensile stress will be generated in the oxide film, and hence there will be brittle oxide cracks and thus unprotective. So, this is the case where the PB ratio is less than 1, and this is the case where the PB ratio is greater than 2. So, there is this flaking off, as you can see that flaking off is taking place, the layer will come out. So, if the PB ratio is between 1 and 2, then actually the it very nicely sits on the base material. So, it works very nicely as a protective coating. So, for example, if you use potassium as a layer, potassium oxide would form, but the PB ratio is much less than unity. So, that means that there will be brittle oxide cracks and potassium cannot be used as a layer. If you use sodium 0.58, the same problem, okay, there will be crack due to tensile stress. Magnesium oxide, again a similar problem, but aluminum oxide, it is between 1 and 2. So, it will very nicely work like a protective coating. That is why aluminum oxide layer is used in many cases as a good protective layer, and aluminum itself is also is much better in terms of corrosion, because a part of aluminum is sacrificed for aluminum oxide formation, and that gives good nice coating of the pure aluminum. Then there is the other ones which are gradually going, like chromium is possibly the last one. Beyond chromium it is greater than 2, and hence you cannot use it as a protective material. So, thus the PV ratio works like a nice guidance in terms of choice of the material. The other point is the reactivity of a metal in seawater, okay, particularly for seaworthy vehicles. This is very important. So, susceptibility to corrosion in seawater, that reduces if you go from, for example, the upward journey. So, you consider Monel. Monel is very heavily used today for all nuclear power plants, where actually the seaside nuclear power plants where Monel is used. So, because of its high capacity of anti-corrosion, and we already said that the advantage of nickel on copper in terms of a high strength. So, both from corrosion as well as from strength point of view, Monel is an excellent material, and the Inconel also is another one. In fact, the secret of making this material is very industrially significant. Not many nations would like to part out with these trade secrets. And then you have stainless steels, titanium, graphite, gold or platinum of course are even better, but you cannot use them. In terms of the susceptibility, what you will be very much cautious about is like using iron, okay, and also aluminum alloy, cadmium. The zinc is highly susceptible, we have seen. So, thus galvanic series gives us a good guidance in terms of the reactivity of metals in the seawater. Now, the corrosions are generally of two types. One is the so called uniform attack corrosion. It is a most common form of corrosion. As you can see, this is a jetty where these anchoring positions are getting uniformly attacked because of the salty condition, and the oxidation and reduction reactions occur randomly all over the surface, and there is a maximum metal loss that occurs in this kind of uniform attack. The other one, which is known as galvanic corrosion, this is very specific case where actually two different types of metals are used for joining or doing some work, like a junction of two different type of metals, okay, like say copper steel junction. Okay. Now, this kind of things happens in boilers, for example. It happens in various types of for example, aircraft, these wiring of the aircraft system, they actually wherever you are actually anchoring these wires, those are actually junctions, and there are also these dissimilar metals in the galvanic series. They actually come in close contact with each other due to mechanical actions, and then the moment that happens, there will be a kind of a cell formation in it. So, one will work like a cathode and the another will work like a anode, and as a result there will be continuous corrosion of materials from one to the other. So, this is something which is galvanic corrosion. This happens because of very specific applications where dissimilar metals or materials are in contact with each other. Then there are intergranular corrosion. This occurs along the grain boundaries in some of the alloys like stainless steel at a high temperature for a long time. If you keep it, what will happen is, for example, in steel, the heat causes the formation of chromium carbide particles along the grain boundary, and then this will create corrosions along in the grains itself, and hence this kind of things is particularly very important when this type of high temperature for a long time kind of a situation comes into picture, particularly for turbine blades and things like that. Then there is the stress corrosion. Now, stress and corrosion, stress corrosion is places where you have a high level of stress as well as you have corrosions due to chemical kind of reasons. So, here the high stress aggravates the problem, okay, because the material gets weaker and there will be more or larger surface which will be exposed, and as a result the two things actually help each other to increase the corrosion process. The other one is the erosion corrosion process, which is a combined effect of chemical attack and mechanical wear due to some kind of fluid motions. For example, propellers, turbine blades, valves and pumps, okay, even in pipelines, okay, where there is these if there are some of the abrasive particles that if the pipeline carries, then there will be erosions as well as corrosions. So, there is a combination of wear and corrosion. So, either stress and corrosion, wear and corrosion, these are the kind of even severe conditions. So, it is not only corrosion, but also something more than that affects the system. Then there is crevice corrosion. It is actually a localized corrosion, occurs due to concentration difference of fluid ions between two regions of the same metal piece. Okay. So, the concentration difference of fluid creates the corrosion, and pitting corrosion and like small pits and hole formation, it generally initiates by scratch on surface and then it grows downwards due to gravity. So, these are various forms of corrosions that are possible in a system. Now, in terms of corrosion resistance, aerated water, this type of material. So, it is the environment which is important, like lead alloy, steel alloy, titanium alloy, nickel alloy, copper alloy, all of them gives high resistance, but aluminum alloy no. Low resistance particularly is carbon steels. Strong acidic medium if it is, then you will see titanium alloy or lead alloy or stainless steel. Aluminum alloy is medium. If it is strong alkaline, nickel alloy, steel and titanium alloy, medium is copper alloy and zinc alloy, and UV generally all alloys. So, one common thing that we can see is that no matter whatever is the medium, titanium alloy is actually good in most of the corrosive environments. So, that is why they are heavily used for corrosive environments. There are certain strategies for corrosion prevention. One is that use material which, of course, based on the PV ratio I said, which can form a good protective oxide layer. Other is add inhibitors, for example, amines and hydrogens which can remove the oxygen, because oxygen creates most of the corrosions. So, use some such inhibitors. Another is reduce temperature, because we have seen that a high temperature corrosion increases. So, reduce the temperature, decrease the corrosion rate. Apply paintings, chemical painting, or go for cathodic protection, like the metal to be protected is connected to another more reactive metal, which gives up its electrons and get readily oxidized in a sacrificial mode. This is why people used to actually carry zinc, okay, in the ships earlier days, because then the zinc will be oxidized, zinc will be sacrificed, but the ship metal will be saved. Magnesium and zinc are more commonly used for this type of purposes. So, these are the various methods for corrosion prevention. This is where we will come to an end, and in the next lecture we will talk about ceramic materials, their classification and crystal structure. Thank you.